case of non-vanishing problem. We'll basically discuss non-vanishing in some certain kind of a uniform way of Hilbert modular functions. This is the joint work of Zhening Wei and Shifan Zhao. At the end, we'll give some kind of brief discussion on our method, which could be generalized to higher ranks or other cases. The non-vanishing problem is very kind of old problem, and it's kind of impossible for me to record all the history. So I just start with one of my favorite examples as a motivation. We'll talk about Brammer's conjecture on the analytic rank of Jacobi varieties. Let J not of Q be the Jacobi variety of modular curve over Q, and assume the grand Riemann hypothesis. Brammer proved an upper bound of the Jacobi variety and the legal rank of the Jacobi variety by the dimension is basically bounded by a scalar multiple of the dimension. And based on this, he conjectured that the algebra rank is equal to the analytical rank, which is roughly 1/2 of the whole dimension. Of course, the first part is BSD. The second part is inspired by this inequality and the general philosophy that the Hell rank the Hell rank does not contribute too much. There are a few like effective work towards this inequality, but all of them should assume the Riemann hypothesis at that time. And then Evanian's law and Sonic use a very new machinery, the low-lying zero stuff, using assuming GLH. They successfully reduced the number to something smaller than 1. Not sure how small it is, but you can compute it. At least it's a big progress to 1/2. And then Kowalski and Michel make a breakthrough. They remove the assumption of the grand Riemann hypothesis. And they get some upper bound, effective constant. Initially, they get something like a 6.5. And after serious work done with Van der Kamp, eventually they reduce the number to something slightly larger than 1. That's a background. And you may wonder, how do we handle this so-called analytical rank? It's due to the work of Eichler and Shimura using modular certain bad prompts. Using their theorem, you can write the Heisel-Wei zeta function of the Jacobi variety as a product of the elliptic modular forms, elliptic modular functions of weight 2 and level Q. Oh, by the way, if you have any question, just please ask. So the analytical rank, the desired inequality of the analytical rank could be reduced to upper bound of the sum of the orders of these functions at the central point. And we have a kind of a trivial observation that the order 0 does not contribute to this at all. Therefore, the upper bound of the whole thing roughly or more or less could be reduced to a lower bound for the order zeros. Give you a lower bound that's kind of one of the motivations to study the non-vanishing problem. Something like this. Given a family, then how many elements in this family such that the central values are non-zero? This 1/6 gives you a positive proportion of the whole thing if you divide the size of the family on both sides. And as an instant application, you can use this result to show that there's a quotient of the Jacobian divided over Q with finite model weight group, and the dimension is not too small. It's as large as 1/6 of the whole thing using the work of Kuliwaga and Lagoshev. And this 1/6 is not optimal. For instance, Evanius and Sanak later improved this 1/6 to 1/4, and this is the best possible so far. And if you have any idea to further improve this 1/4 slightly, just slightly, you would be able to prove the non-existence of lambda 0 zeros for discrete functions of quadratic characters. That would be a very difficult problem. So currently the barrier so far is 1/4. And the non-vanishing problem we've been talking about or in this talk that we are interested in is the following. We consider we consider a set of a finite set of automorphic representations, or if you want, automorphic forms, and we want to find some constant such that the number of representations with non-zero central values would have a positive lower limit when the size of the family goes to infinity. Here we highlight that the size goes to infinity, and you will see why we highlight this, because in the history we always do certain specific aspects. For instance, the size goes to infinity means the product of the weight and the level goes to infinity. Typically, people will fix one of them. For instance, in the initial um, problem, the weight is fixed because the weight is just 2, and say vary the level. For instance, when the base field is Q, but due to the work of Hwaski, Michel, Van der Kamp, Van eventually get the positive proportion as 1/4. And this has been generalized by chart-based to total real fields. Again, the best record is 25%. And you may wonder, what if we fix the level and vary the weight? For instance, let level be trivial and vary the weight. This is a much harder problem. It was until like years ago, that law gave the first non-vanishing result, and this positive proportion is not quite computable. We just know there's some positive number, but we don't know how large it is. And recently, Bakanova and Frelenkov give the best record so far, which is 1/5, slightly weaker than 1/4. But this is the best result that we can prove. And we'll see why this is a natural barrier or limit of the current approach. And at least we hope to generalize things to Hilbert modular forms, because Hilbert modular forms is a natural object to study, and it will provide some more difficulty that does not show up in the Q case. And you will see, at least you will see their method is not quite convenient for the Hilbert modular form case. And we may also consider this family for other forms, like mass forms, if you prefer. Of course, that's not our focus today, so we will briefly mention there are some work over mass forms as well. So what we will do, we will consider, as we have claimed, we will consider normalized the new forms of a total real field of a prime level Q and a certain weight. In particular, the weight should the weight may not be parallel. You may roughly think this family is a generalization of the very favorite family of elliptic modular forms. Our goal is to find some function, arithmetic function, depending on the weight and the level, so that when the product of the weight and the level goes to infinity, this guy would have a lower limit, which is strictly positive. And now, actually, we want this guy to be as large as possible to compare the best known results in the weight or the level aspect respectively. And by the way, we'll use the notation like a norm, but we really mean roughly the Archimedean conductor of the representation, just the product of the weights. And here's the main result. We do find such a function. It's kind of complicated, and we will explain in certain special cases so that you will have a global feeling about this result. In particular, we find a lower bound. This lower bound has the following property: when you fix the weight and just vary the level, the lower bound has a limit like 1/4. And if you If you fix the level to be trivial and vary the weight, you get 1/5. So this is basically a generalization of the work of Bakanova and Fredlenkov to the real fields case. And more importantly, I think the key point is that when you put no restriction on the weight and level, just like their product go infinity, you are still get some positive proportion, like 1/100. So individually, we have the following. Um, this reflects the title that we call the uniform non-vanishing. When there's no constraint, you get 1/100. For instance, why we would think this is kind of independent or kind of a new result, because the major difficulty comes from the following. If you just fix the level and vary the weight, and level is non-trivial, and you will see some kind of bad things. The bad things come from the old form, because in this case, the old form will contribute to as another main term. For example, let the level be 2. And in this case, the old form contributes significantly. So you really need to take care of those terms. And this kind of results was only known under the grand Riemann hypothesis due to the work of Ivanyan, Low, and Sanak. And they can prove a much better bond 1/8. But it was not known without the Riemann hypothesis. That's our first application. And again, if you just fix one of the aspects, you will get some strong bond, strong in the sense of the current record. In the level aspect, we recover the work of Chota base. In the weight aspect, we generalize the work of Baganova and Fredlenkov in the trivial level case. And you may wonder if the level is non-trivial, but we still vary the weight, what would be the lower bound explicitly depending on the level? It's something like this. It's not best of, it's not best, but if you, for instance, you see a huge discontinuity on the level aspect. When Q is here, when Q is 1 here, you plug it just a 0. So this formula does not work for Q equal to 1 case. First Q equal to 1 case to be handled independently, we'll get 1/5, which is much larger. For general Q, we only get this formula. So when Q is super large, you roughly get 1/10. But in general, you get 1 over, say, 100. That's basically our main results. Questions so far? 3, 2, 1. Okay. Now we will go. We will start to talk about the proof. The idea is pretty simple. It's just the application of the Cauchy-Schwarz inequality. Here's the idea. We will compute the average of the central values. It's difficult to just compute the average itself. So typically we'll put some weight, and this weight is certain L value at 1, and we will call it the harmonic weight. At this moment, just ignore this weight issue. And we'll compute the average, and luckily it's not too hard to compute. We can get the main term, which is roughly scalar multiple of the whole size and a certain L term. Similarly, we can compute the second moment. Second moment means we put a square here. Again, we get some main term and some L term. This is also not too hard. And now the main, because we have a square here, the main term will actually give you something larger. It's roughly the scalar multiple of the size multiplying log of the size. So the idea is the following. We apply Cauchy, noting that only the non-zero central values will contribute. So we can square the first moment at 2 parts as the upper bound. One is from the non-zero thing, and the other is the second moment. So the number of the non-zero naturally has a lower bound as the square root of the first moment divided by the second moment. So ignore all those error terms. You get roughly the main term squared of the first moment divided by the main term of the second moment. So plug everything here. You will get some constant. You will get the size. You will get a log on the in the denominator. So let's copy it here. Let's copy it here. Because this is just an indicator function. We can rewrite the left-hand side as the sum over the family, where only the non-zero central value representations like contribute. So we get this inequality. Uh, Ignore this colored part. We will get what we want here. But log of the size is not too small because the size would be very large. So we will almost get the positive proportion, just lose by a log. If you ignore this blue color part. So then our task is to handle these two issues. One is to remove this harmonic weight, and one is to remove the log. So we need to modify our arguments. And the reason that we can eventually succeed is the following. We can make use of some analytic techniques to remove the log using properties of Hack operators. It's called a modification. And we can using representation like advantages to remove the harmonic weight is a one case special case of allowance functoriality. Eventually, we need the fact that the symmetric square of a GL2 representation is also an automorphic representation. You can that's the key input in the whole game. Questions so far? Okay, so let's work with this right color part first. We aim to remove the log on the right hand side. Recall that um, this guy comes from the calculation of the first moment and second moment. The first moment is roughly the size. The second moment is roughly the size multiplying log. So we will introduce a hack operator in the first moment. The operator will change the main term slightly. It's just a rescaler the main term dividing by the square root of the norm, and it modify the main term of the second moment in a similar way. You get a square root on the denominator, and you get the divisor function. Divisor function in the numerator which is kind of harmless, because eventually we can take n to be a prime or prime squared. So this you can just ignore this. Roughly, if you apply hack operators in the average, you will change the main terms just by some square root. So the idea is the following: we will divide the square root on both sides, so that this guy would be the size dividing the norm. And if we summing over the norm up to the size to some power, you will get a log. And here you will get another log. This log will cancel the log from the main term, so that we will win to eliminate the log. This is the idea of modification. Eventually, I think it dates back to Stolberg. And in practice, we will not just work with a simple eigenvalue value. Instead, we will consider linear combination to optimize the whole thing. And this is a linear combination that we will use. Ignore this integral thing. It's just a truncation. And ignore this relevant is certain nice arithmetic function as a weight. This is a mu function, the Mobius function. This is the eigenvalue. Roughly speaking, the whole thing is basically the truncation of the reciprocal of the L function at 1/2. So in this case, sorry, there's no wire. In this case, you plug the linear combination of the Hack operators into the average, you will get the first moment whose main term is roughly scalar multiple of the size. And the main term of the second moment would be scalar multiple of the size multiplying log of the size dividing by log of the parameter. This parameter is this guy, is some power of the size, which will be determined later. And apply this kind of weighted versions. You will see using Cauchy-Schwarz, you will see the lower bound of the positive proportion would becomes the first moment squared divided by the second moment, and which is roughly of the form some constant multiplying the size divided by the ratios of log. Initially, we do not have this log of c, so we lose a log factor in the denominator, so we cannot get positive proportion. By using this kind of modification trick, we get a log in the denominator, and we can hope that c could be large, so that the whole thing, the whole, I think this is purple color part is a constant. Therefore, we will get a constant multiplying the size so that we get a positive proportion. That is the idea. So you can see the whole idea is kind of simple. But now the problem is the following. How can we choose this kind of C? How large is it? We need to see as large as some small power of the whole size. Okay, we also say nothing about the old forms, but for the moment, let's ignore it. Um, to compute this kind of modifier weighted moments, we can just open it up to a linear combination of the eigenvalues. Although in the second moment is not just the original eigenvalue anymore, it's slightly different due to eigenrelations, but we can write it in a general form. So the whole problem will be reduced to find a very good asymptotic formulas for the lambda weighted first moment and second moment. And eventually these main terms are easy to compute. But the major task is to describe the error terms. We want the error terms to be as small as possible so that we can choose our parameter C as large as possible. The idea is the following. Recall we have this lower bound and this C is the parameter. We want it as large as possible, but it cannot be too large because otherwise the error terms will be larger than the main term. So it has some kind of restriction, and we need to work out this restriction. I need to claim the first moment is kind of simple, so let's ignore it. Let's mainly focus on the second moment. This is a major task. And in practice, there's a very lovely and powerful formula to compute the second moment for arbitrary, not for arbitrary, for arbitrary weight. And it's the so-called Kuznetsov's formula. It's a well-known formula, but it's not published. It's in one of these preprint, and it's a really useful formula in classical studying of a non-vanishing problem. Roughly speaking, you can compute. It gives a precise formula for the second moment of the L functions. For instance, you take S1, S2 to be 0, you get the weighted second moment. On the right hand side, you get a bunch of main terms. As you can see, it's kind of complicated, and plus an error term. This error term is the major interest. We want to bound this error term. The error term is of this form. It's pretty complicated. It's a combination, linear combinations of this gamma functions, certain special functions, in particular the hypergeometric functions, and we cannot take S1 and S2 to be 0 as we want, because you can see immediately the main term will blow up. Because zeta function is a pole here. And also, for instance, the error term also blows up because we have a cosine pi over 2 on the denominator. So you need to take care of them. And eventually you will get certain hypergeometric functions and their derivatives that you need to handle. this is the idea of Bakanova and Franenkov, where they get to, that's the reason they can get 1/5 in the weight aspect, because they develop some, they used a certain nice idea. They used the Liyang green method use in a nice way to handle the hypergeometric functions and their derivatives. Eventually, they can prove the lower bound uh, like this. That means they get a square root saving in the lower bound. And this square root saving will give you immediately 1/5. And that's why we regard it as a natural limit or natural barrier in the level in the weight aspect. Because in general, we cannot expect more than square root saving, right? Again, our goal is to generalize things to here the module forms at least, and hope to study non-general level case and the general weight case. So first of all, Kuznetsov formula is not available at all anymore because it only works for level 1 case and over Q. And why do we still expect a square root saving in the general case? We will provide two strong intuition from different aspects. One is from micro-local analysis. It tells you roughly, or actually for a simple reason, we must have a square root cancellation. For instance, if you use micro-local lift vectors using a certain regularized relative trace formula, you will see immediately the error term as the square root saving. However, the main term or on the left side, the sign is not precisely over this family of weight k level q. It's actually slightly larger in neighborhood. It will run. You cannot exclude the possibility from mass forms of a particular or of similar eigenvalue like a 2k and 2k plus capital over 1 and level q. Because we do not know good information about spectral gaps, so we cannot exclude that possibility. That means we make the analytic side very easy, but we have no idea how to describe the spectral side easily. That's one motivation, at least. Roughly, we will get the square root saving using micro-local analysis. Another is from geometry, from arithmetic, using Grozaghian formula. You can compute the average of the base change function. In this case, the Rosaglia formula will give you a precise formula for the error term, and then using kind of a trivial bound for Laurent function, Laurent polynomials, you get the square root saving. Roughly speaking, you get a closed formula for this average, and you get the main term, you get the error term as a finite sum of Laurent polynomials. Using trivial bound, you will get the square root saving. You can see this guy and this guy look quite similar. Just ignore this quadratic character. But this character comes from arithmetic reason. Without this character, you would not have Laurent polynomials just like this neatly. You'll get something more. And it's our task to describe these error terms in terms of these Laurent polynomials or those something more. And then we expect some trivial applications of the Laurent polynomials or those similar elementary similar functions will give you the square root saving. That's our idea. Without using the Liyang method to study differential equations. And the major input is from representation or from harmonic analysis. We'll consider so-called relative trace formula. We start with a nice function on the upper half plane. Associated with this nice function, we can define a kernel function of the generalized Hegel operator. The kernel function is just a sum over the rational points. If you choose this function nicely, for instance, like we will choose it, we are defining over the dial. The Archimedean places are just a matrix coefficient of discrete series of weight k. At the finite places on the level aspect, we just take it to be standard growth vectors. And using these functions, you will see this average over rational points could be written as a bilinear structure. summing over exactly of the modular forms of weight k and level q. This double sign refers to the size over the whole here the modular forms, both new forms and old forms. This is the eigenvalue. These are just here of the modular forms. And then we will use this guy, we'll plus this guy into integral like this. This integral is the Hike integral for L functions. That means we will not write an L function as a Dirichlet series. Instead, we'll write it in terms of a Hike integral. This is the integral over along the y-axis, the Main transform. And unfortunately, well, you have two expressions of the kernel function. Plug it into this integral, you will automatically get a formula because of these two expressions. One of the expression, this one, will give you automatically the lambda weighted second moment. And then our task reduces to on the contribution by plugging the geometric description of the kernel into here. So it has nothing to do with any automorphic data. It's just bounding the integrals of the sums or the Main transforms of the sums. So it looks like something doable. Here's a major issue from analytical viewpoint that this integral does not converge at all. So we will need to do certain kind of a regularization to make it converge. Roughly speaking, due to certain manipulations, we can show this can be turned into a regularized converged integral, and then we do Bragg decomposition in the geometric side to handle the average over the rational points. Roughly speaking, you can divide PGL2 in terms of the upper triangular matrix and lower triangular matrix, and all the other kind of matrices will contribute as an error term. So we get the regularized segment moment. Spectral side is for free, and now we need to compute the geometric side by plugging the rational points like average each thing. And again, just we only need to describe the error term because the main term is kind of simple. The error term after Bragg decomposition to be written as a rational as a sum of this explicit integral. Recall the function itself is very explicit, and the sum is over all the rational points. However, you can eventually show this guy is basically a finite sum. It's basically a finite sum. Moreover, because the function is defined over dials, you can write this integral in terms of local integrals. So chaotic integrals and Archimedean integrals. The chaotic integrals is very straightforward. Sorry. The chaotic integrals is very straightforward. It will give you the divisor function, just a counting. Will give you a divisor function. This is a phenomenon already observed from Kuznetsov's formula. And the key ingredient is the Archimedean component. When this FV is equal to R, in that case, the local integral becomes something like this. This is the counterpart of the hypergeometric function and its derivative in the Kuznetsov's formula case. So we need to compute it and then estimate it. By certain brute force calculation, you will see luckily these integrals could be written as P of U. P of U would have the following expressions. It depends on the size of U. When U is small, for instance, when you let's say that this disk, P of U is given precisely by Lorentz polynomials, as we have expected from Gonzaga's formula. And using the trivial boundable or well-known boundable Lorentz polynomials, we immediately get the square root cancellation. That's good. And when the points is where the points running over a fractional idea, when the points is not in the disk, is not given by the Lorentz polynomial anymore. It reflects something non-arithmetic. Because we just compute something like a second moment rather than the base change of function, there's no quadratic character as an arithmetic input. So we cannot expect everything to be purely arithmetic. In this case, we will do certain kind of meromorphic continuation, and still we are able to compute this integral in terms of around functions. It's something slightly more complicated than around polynomials, but not too complicated compared with Hilbert geometric functions. Again, we can bound those things in an easy way, and then put this together, you will get a square root cancellation. And plug the square root cancellation here. You can see roughly you can take C to be the whole thing to 1/4, and that's why you get 1/5 immediately in the weight aspect. In this case, we assume the level to be trivial. Um, Otherwise, we need to handle the contribution from old forms, which is kind of tedious. We are not discussing it here, but this reflects the rough idea of our approach. And we almost done modulo this harmonic weight. Now we need to handle the harmonic weight and tell you how to remove it. The idea is from Kowalski and Michel. We can write this L value in terms of Dirichlet polynomials, where w of x is the main term, and this is a short polynomial, and this is a longer Dirichlet polynomial like this, and we will bound this guy roughly. This is our major enemy. The symptotic formula there, you will see we only need to bound this part because the blue color part is roughly 1, so we are just doing nothing so far. And uh, upon change the modifier, because all those things are constructed from Heisenberg values. So just change our initial linear combination of the Heisenberg values as a modifier. You will absorb those terms in the previous case. So we only need to handle the contribution from this tail. The idea is the following. It suffices to establish such a upper bound for the product of the modifier and the signal and the central value. As long as we have some bound like this, we can show easily that the contribution from this part is trivial. Not trivial is more. So typically people will get those kind of bounds via a certain kind of subconsty. In our case, we need a subconsty like this. And this kind of subconsty is not strong in individual aspects. For instance, the level aspect is just a convexity bound. So this 1/4 just follows from the functional equation, not a big deal. However, if you require the dependence on the weight as well, it's a much harder. This 3/8 reflects the so-called Burgess bound. We know this bound individually, but the dependence on the level is much worse. Roughly speaking, we do not know those kind of subconscious bounds when the base field is not Q. That might be one of the difficulty that people do not generalize since you hear the module forms. So how do we handle this? Um, instead of proving such a hybrid subclass bound, we will bound the product of the modifier and the central value directly. We'll use the amplification to get those kind of saving. That means if you imply amplification in the modification of the second moment, you will get a non-trivial upper bound for the product of the modifier, the second and the central value. In fact, we save much more, not just some small delta. We get something larger. And this is of course sufficient. And plug everything to Kowalski-Michel's manipulation of the harmonic weight, you get immediate. You get 1/5 without harmonic weight. This is one of the particular case of the main theorem in the trivial level case. That's roughly what I want to talk for the subject. But I want to use the last two slides to show at least to give you a rough feeling that these harmonic analysis techniques using the so-called relative trace formula is much more general. You can think that here of the module form case of this non-vanishing problem as a GL2 plus GL1 case where the GL1 is trivial. Then you can use this idea to generalize the non-vanishing problem to GLN plus 1 cross GLN. The idea is kind of similar, almost the same. You start with a nice function on GO on an arbitrary group. For instance, you take G to be GON plus 1, and then you form the Heck operator, just an average of the right translation. And this Heck operator acts on the L2 space of certain central character, and it's representable by the kernel like before. It's just the average of the rational points. And also it has a spectral decomposition as a bilinear form constructed from the cusp forms and the direct integral of S-instance series. If you want, you ignore the S-instance series. So this is basically average of the cusp forms. So you have an expression identity here. Typically it's called pre-trace formula. And then plug this identity into any reasonable integrals. You will get an integral, you will get an identity as a formula immediately and for free. That's called a relative trace formula. In this case, you can plug the expression of the kernel functions into this identity, into this integral. This integral is the integral over GLN weighted by two cusp forms on GLN. So that if you plug the spectral decomposition of the kernel function, you will get a second moment of GLN plus 1 cross GLN. Weighted, for instance, you can choose your test function f to put Hagen values here. And the geometric side will be the main task. As before, you can work hard to find the geometric side to be represented by certain simple L functions or ratios of the ranking subgroup functions, and then plug some L terms, again, certain special functions over rational points in a dimensional n space. This special functions is certain kind of generalization of the Lorentz polynomials, for instance. And then you handle those kind of L terms and get some capacity for GLN plus 1 cross GLN, like Paul Nelson's case. And you can get the simultaneous non-vanishing in this case, because we have a main term, we have an average of those products. That's why we can get the simultaneous non-vanishing for those. Although in this case, we are not able to get positive proportion because we do not have functoriality in this case. We only have the symmetric square lifting or precisely the adjoint lifting for GL2, but not for GLN. So we cannot remove the harmonic weight. And that's why we cannot get a positive proportion. As a very concrete example, we'll give you a soft way to prove a simultaneous non-vanishing over GL3 spectrum. GL3 cross GL1 and GL3 cross GL2. You apply all those previous tricks into this particular integral. This integral is over GL1 and y running over GL2. In particular, the spectral side is precisely the sum of the GL3 cross GL1 L function multiplying GL3 cross GL2 L function, running over the GL3 representations. And you can find certain nice test function so that the geometric side has only one term, and which is the main term, which is not zero. So immediately you know there are infinite many those terms by varying the level, such that the product is non-zero. Unfortunately, we do not know how to specify or how to describe the spectral side. It's kind of an uncertainty principle. You can make one side easy, but the other side will be crazy. So just for the reason of non-vanishing, you only need to make one side easy. For instance, make the geometric side easy. And if you want the positive proportion, unfortunately, you have to work hard to make both sides kind of explicit. That's roughly the philosophy of the whole idea. Thanks.
Okay, stop recording.